Hello everyone, I'm Wenyao Li, and today I'm going to be presenting my project, which is hybrid electric vehicle with both speed and torque coupling. And the goal of this project is to find the optimal trade-off between acceleration performance and emission. And the acceleration performance is measured in the acceleration time, which is the time it takes to reach a certain speed. And the less time it took to reach that speed, the better the acceleration performance. And the emission is measured in the amount of harmful particle, such as carbon monoxide released in grams every kilometer traveled. And the less emission, the better. And the input variable will be engine and motor power. And here's just some introduction to hybrid electric vehicle. In this type of vehicle, it's driven by both an engine and a motor. And because in this vehicle, the motor provides part of the power, so the engine doesn't have to be that powerful, and it improves the mileage. And as well the motor, because it's controlled by electricity, is capable of much precise motion and better acceleration. And in this particular HEV, it has a parallel drivetrain, and this means is that both the motor and the engine are independently connected to the transmission, and it's capable of coupling, which is combining the output of both engine power plant for the better performance. For example, if a motor runs at a certain speed and the engine runs at another speed, when we add the speed coupling, the result we get is the sum of the motor and the engine speed. The same could be done for torque. And here's just a simple block diagram of typical parallel HEV vehicle. And the vehicle I used in this project is Toyota Prius, because it is one vehicle that has both speed and torque coupling features, and this is what I used in my simulation. And here's just some of the basic characteristics of the Prius. And for the first design of experiment, I tried to optimize acceleration time, and as a function of both engine power and the motor power. And the acceleration time I used was the time it takes for the vehicle to accelerate from 0 to a speed of 60 miles per hour or 95 kilometers per hour. And I used a whole bunch of combination of engine and motor powers, and the engine power is shown in the first row, while the motor power is shown in the first column. And as we should note that engine power has a much greater impact on the acceleration time than motor does. And as you can see, here's just a graph of the acceleration time with respect to engine power, and the greater engine power means the less time it takes to accelerate to the final velocity. And the reason I only have this graph at one motor power rating is because the effect of motor on the acceleration time is so negligible that the plot will basically overlap and be extremely hard to see. And for my second design experiment, I tried to optimize the emission. And the emission is measured in grams released per every kilometer traveled by the vehicle. And the three harmful particles are hydrocarbon, carbon monoxide, and nitrous oxide. And once again, we can see that the motor power has a tiny effect on all three levels of emission, but the effect, even more peculiar, is that the effect is cyclical, meaning increase the motor power, and all three levels of emissions goes up and down, up and down. And as for the engine power, the engine once again has much greater impact on the emission and has a positive relation, meaning increased engine power leads to greater emission, which is expected. And we found that motor power operated at 41 kilowatts actually reduces the emission from the baseline motor power of 31 kilowatts, and thus I chose my motor to operate at 41 kilowatts, and this is this motor size I chose for my design. And in here, I put the level of increased emission at a different engine power as a percentage of the baseline emission. As we can see, for example, for carbon monoxide, when we increase the engine power from the original 43 kilowatts to 53 kilowatts, for example, the emission level of carbon monoxide increased 23%. And also if for hydrocarbon, if you increase the engine power to 48 kilowatts, for example, from the original 43 kilowatts, we have an increase of emission of 13%. As for acceleration time, I did the same thing, except this time it's not measured in acceleration time increase but decrease, because decreased acceleration time leads to better performance. So for example, if we were to increase the engine power to 58 kilowatts from the original 43 kilowatts, we have a 30% reduction in acceleration time. And on the other hand, if we were to increase the engine power to 63 kilowatts, we have an acceleration time reduction of 16%. And finally, to find the optimal trade-off of acceleration time to emission in level, I use the ratio to calculate it. Basically, what it is I use the decrease of acceleration time in percentage to the increase in emission level as a percentage. And so I took the percentage of acceleration times decrease to the increase in emission levels increase. So what this ratio does is that it tells us how much acceleration performance, how much improvement of acceleration we can get at a certain increase to the increase in emission level we can get. For example, if we were to increase the power to 48 kilowatts, we have a acceleration performance to emission of hydrocarbon ratio of 0.38, and the higher ratio represent greater improvement in acceleration at a to the emission level. So, and for the results, I found that the engine power if you operate the engine at 48 kilowatts and then motor power of 41 kilowatts, we have the optimal acceleration performance to emission level ratio. The discussion. So once again, the motor performance is extremely unexpected, and it's extremely erratic. And finally, if we had more time, I would be able to change the gear ratio and transmission ratio, and it could possibly lead to greater vehicle performance and improve emission. But for now, I think I found an optimal trade-off between acceleration time and the emission level. And I found the optimal sizing of the drivetrain with respect to motor and the engine power. And thank you.